Japan. I also learned from him a lot. Okay, today I will use 2 journal papers to explain my lecture. Okay, he is the first author of 1 journal paper. That's why I'm introducing him. Okay. Okay. So I will change my slide. Sorry. Can you see this Google map? Can you see?
Yes.
Okay. So now I'm staying in a hotel, okay, away from Tokyo. I'm in a business trip. Okay? After this lecture, I'll go to mountainous tunnel for tunnel technology development. Okay. Now I'm here, not so far from Fukushima nuclear power plant. I'm in Fukushima prefecture now. Okay, here Tokyo. Now I'm in a rural area, okay, away from Tokyo. So can you see this deep trench? Okay. So this trench caused a very big disaster in 2011, nearly 10 years ago. Okay. So just like your country, we are in the same fate. Where is your country? Same kind of situation, okay? So we Japanese people suffer from earthquakes a lot, but we try to overcome that difficulty. That's why today I hope you can learn some my essences or lessons which we learned, okay, to overcome this difficulty. Okay. Okay. So. ちょっと待ってください。Okay. Next, can you see this picture? No? Can you see?
Yes.
Okay. So I said that now I'm away from Tokyo. And I'm in a rural area near, not so far from Fukushima nuclear power plant. So you can find a kind of residential area, okay? Much. Can you see this structure? 30 minutes ago, I took this picture from my hotel room, okay? Can you see Shinkansen train? Okay. But
Yes,
2 different
can.
colors Shinkansen
Yes,
trains are connected
can.
together, and it was running on concrete structures. Okay, so it's called elevated bridge or viaduct. Viaducts. Okay, it's a layered structure. Okay, you can see columns or beam and etc. Okay, can you identify white color of columns? Yeah. These columns have been retrofitted by steel jacketing method. Okay. Okay. So without these retrofitting in big earthquake, this huge railway viaduct can collapse. Okay. Yeah. These columns have been in big earthquake. This huge railway viaduct
Your voice is.
can you see this paper?
Okay. Thank you.
I sent
Yes.
this journal paper to Dr. Retono, so I hope it's shared already, and you can refer it anytime. Okay. We will explain the my core points of my today's lecture utilizing this paper. Okay. The title is Seismic Damage and Seismic Rehabilitation Techniques for Railway Reinforced Concrete Structures. Okay. The first author is Dr. Ishibashi. Okay. I showed his face picture already. Okay. This is included in Advanced Concrete Technology, published by Japan Concrete Institute, JCI. Actually, this is the level of this journal may be very high. Okay, I think one of the top level journal in the world, but due to globalization or very severe competition, the impact factor of this journal is a bit decreasing. But anyway, this is invited paper in that top level journal. Okay? So, of course, our country, Japan, or your country also, Indonesia also, is prone to earthquake damage. But earthquake happens so often. Okay. In the field of concrete engineering, 1978, so nearly 40 years ago, a big earthquake was a trigger, okay? Because this Miyagi Prefecture earthquake in 1978 was the first earthquake to cause damage to railway concrete structures in Japan, okay? After that, maybe some of you know that in 1995, a very big earthquake happened in Kobe. Okay? It's called Kobe earthquake, okay? Which caused catastrophic failure, actually shear failure of columns of RC viaducts, okay? Carrying the Shinkansen bullet train in my picture taken 30 minutes ago, okay? So, but these two, especially 1995, Kobe earthquake was a trigger to change seismic design standard, okay? Today I will explain such kind of story. Okay. So, here, again, in 1978, a big earthquake near Sendai area happened, okay? As a result, the seismic design standard of railway structures was revised in 1983. So after that, the structures designed based on this revised design code showed higher performance against earthquake. Hi. Okay, so first of all, maybe you should see what kind of damage happened in earthquake, okay? I have shared this PowerPoint file also, okay? Maybe I will not use all of the slides today. I will refer some my important pictures or important my tables, etc. Okay. In the latter half of this PowerPoint file, this scenario is included damage analysis of RC structures in Kobe earthquake in 1995. Okay. If I have sufficient time, I'll try to explain this scenario also. Okay. First of all, let's see the catastrophic damage caused by Kobe earthquake. Okay. It happened in 1995, January, very cold season in Japan. And the time was also important, okay? 5:47 a.m., okay? 30 minutes before 6 a.m. It has a meaning, okay? The Kobe is near here, okay? The very huge earthquake. Magnitude was that large, only 7.2, but it happened just under mega city, okay? Okay, so first, please have an image about the damage. So Kobe earthquake caused a really catastrophic failure. Okay, maybe it's a bit difficult to imagine the original structure. This is also okay. So beam and slabs are healthy, but the columns supporting upper structures were totally failed. Okay, by shear failure. Okay. So if you have learned the basic matters about concrete structures, but you can imagine what happened. Okay, so shear failure of columns happened. Then the original level of upper structures decreased a lot. Okay, so we should prevent this kind of catastrophic shear failure. Okay. Okay. Yeah, I'll go back to the journal paper. Okay, in chapter 2, seismic damage of railway RC structures. So these authors, Dr. Ishibashi, etc., explain a kind of history of damage, but I'll skip some parts. Okay, let's go to second paragraph. Okay, here, due to Kobe earthquake in 1995, many columns of RC viaducts suffered shear failure, as you saw in my PowerPoint file. Okay. As a result, the beams and the bridges that hold up railway tracks suffered serious damage. Okay, the failure mode of these damaged structures became shear failure before yielding of the longitudinal reinforcement of column members. Okay, this is important. I'll explain more in detail later. Okay, so yielding of longitudinal reinforcement is very important to absorb earthquake energy. Okay. Hi. Here. Fortunately, as the earthquake occurred in the early morning, as I explained already, it happened in 5:47 a.m. Okay. But that's why accidents involving trains falling from RC viaducts and bridges did not occur. Okay. So, do you know that Shinkansen in Japan, Shinkansen operation starts at 6 a.m., 6:00 a.m. Okay. Do you know that? It stops operation at midnight and starts operation at 6 a.m. Those 6 hours is very important time for maintenance. Okay, so every day the track condition So RC structures, RC viaducts collapse. There may be Shinkansen with high speed, or maybe went down on the ground. Okay, but it will run. But we should think that God gave us time to improve our social system. Okay, I am thinking in that way. Okay. Okay. Okay, that's why, anyway, we needed to improve many things, design code, or we needed to retrofit a huge number of existing structures, etc. Okay. Hi. Sorry, I will jump to the this figure, okay, to explain the importance of energy absorption or importance to prevent shear failure. Okay, can you see this slide, figure 27? Okay, so I'll explain slowly. Okay, so what's the what's this? What's the title of this figure? Figure 27. Example of relationship between strength ratio and plasticity rate during cyclic loading of reinforced concrete column, RC column. Okay. So what's the vertical axis? Strength ratio P over P yield. Okay. Here 1, here 1.5. Okay. So P yield means the load to get yielding of RC column. Okay. So here 1. Okay. So 1.3 or something higher than 1 means that the P load exceeded P yield. Okay. So load became higher than the yielding load. Okay. Can you understand the meaning? What's the horizontal axis? Okay. Plasticity rate, delta over delta yield, yielding displacement. Okay. So 10 means that 10 times larger than the yielding displacement. Okay. Okay. So blue one is the reinforced concrete column with sufficient hoop reinforcement. It shows ductile behavior like that. Okay. This is energy absorption area. Okay. Load and displacement. So that's why after yielding, by deforming like that, this RC column can absorb lots of energy. Okay. What's red color? I'll explain later. The reinforced concrete column retrofitted with a spiral reinforcement inside the longitudinal reinforcement, special technique developed in Japan, actually like that. Spiral reinforcement is installed inside longitudinal main reinforcing bars. Okay. It's called inside spiral reinforcement. Okay. By applying this special technique, it showed much larger ductility, deformable performance. It will absorb more energy. Okay. Finally, I want to emphasize that what will happen when shear failure happens. Okay. If you remember my explanation, shear failure happened before yielding. Okay, or reinforcement. So it will fail like that suddenly. Okay, before yielding, before reaching 1 in vertical axis, it will fail. Okay, so without showing sufficient energy absorption performance, it will collapse. Okay, that's why we should prevent shear failure, and we should pursue, we should expect, we should achieve this ductile behavior. That's the point. Okay, do you understand? So I'll explain too much, but Are you following me? It's okay? Okay, so I'll go ahead. So I will go back. Okay, so today maybe I cannot explain all the retrofitting methods or all the details, but this paper summarized very well about the damage situations and also retrofitting techniques. So please study, okay, if you're interested after this class. Okay, but I'll try my best to explain the essential parts of this paper. Okay. Okay. So I briefly explained the seismic damage of railway RC structures. Okay? Especially shear failure should be prevented, should be avoided, okay, by appropriate designing, or in the case of existing structures, we should retrofit, okay, appropriately to prevent catastrophic shear failure. Okay. Hi. Okay. Then. OK。ちょっと待ってください。So, can you see this map? Okay. はい。Actually, this Hokkaido Island, the top north island, is located not here. It should be here, but according to the arrangement of journal paper, it's here. It shifted here. Okay. Before, Japanese government was operating this network system, but around 30 years ago, it's divided into private companies. Okay? I was working in this East Japan Railway Company, biggest railway company in Japan. Okay? Here in this section, I will try to explain the history of the efforts of civil engineers to overcome this situation. Okay. So again, in 1995, Kobe earthquake happened near here. Okay, the catastrophic failure of reinforced concrete viaducts happened in this region. Okay. After that, Japanese government instructed to start retrofitting of existing structures, huge amount of existing structures. Okay, most of them are over constructed before revising design code. Okay, so I explained that the railway design code was revised in 1983. Okay, the many structures were constructed based on old design code. I mean, before 1983. Okay, it means that those structures must have lower seismic performance, and those should be or must be retrofitted appropriately. Okay, appropriately. Okay. Okay, I will tell you the situations. So first, the Japanese government ordered or instructed to retrofit the structures in mega city areas like Tokyo, Osaka, Nagoya, Sendai, and this area, Kyushu, okay, Fukuoka area. The railway companies started to retrofit those weak structures. Okay? It means that other regions, for example, the area I'm staying now, okay, it's away from a mega city area, right? So many structures away from mega city areas were left unretrofitted. Okay. But again, in Japan, maybe in your country also same, earthquake can happen anywhere, okay? So the risk of that kind of catastrophic failure exists almost everywhere in Japan, okay? So after finishing the retrofitting in mega city areas, railway company decided to retrofit all the structures, okay? Step by step. Okay? So now it's almost completed, but not perfect. I can say 90% finished. Okay, but still 10% very difficult structures are remain. Okay, and retrofitted. So we should continue our challenge. Okay, so that's the situation in Japan. Okay. Hi. Such kind of history is explained in this section, okay, with table 1. So if you're interested, please read it. Okay. はい。で、here, sorry. 3.2 main, sorry, 違うな。I'm sorry. Yeah, sorry. 3.1 basic concept for seismic rehabilitation is summarized. Okay, so let's share the basic concept first. After that, I will go into the details of seismic retrofitting, etc. Okay, 3.1 basic concept. The basic concept of seismic rehabilitation or retrofitting is to prevent, again, shear failure of column members, okay, caused by large earthquakes resulting in the collapse of RC viaducts and bridges, which are catastrophes that have occurred in past earthquakes. Okay? To enhance the seismic capacity of the whole structural frame, the aim is to increase the ductility capacity of column members through seismic rehabilitation in order to allow better absorption of earthquake energy. So I hope many of you remember figure 27, okay, showing the load and displacement relationship. Okay, so we need to enhance the ductility, okay, of column members. Okay, column is the vitally important members. Okay, はい。で、okay, this sentence is also very important, but enhancing the flexural capacity, flexural strength of the column members should not be done. Okay, why? The reason for this is that if the flexural strength of the column members is enhanced, future earthquake damage may occur in beam members and foundation members. Okay, so it's a bit difficult to understand this one, but I'll try to explain. Okay, so in summary, ductility, again here, ductility should be increased, okay? Avoiding shear failure, okay? But flexural strength of the column should not be increased, okay? Is okay? Only ductility should be improved. Strength should not be improved. Okay? Hi. Why? Since repair and strengthening of beams and foundation is more difficult than column members. Okay? So it is considered important to restrict damage only to column members. Okay? To have a clearer image about that explanation, again, I'll go back to the slides, okay? So I hope you can see this PowerPoint file, okay? You can see very severe damage of columns. But you can find that the beam are healthy, right? You cannot see the condition of underground foundation, but no damage at all, okay? So damages were concentrated in columns, okay? Okay, so this is a kind of schematic figure of RC frame structures, RC viaducts. It's a bit difficult to imagine, but these are columns, okay? Can you see this one? These are columns. This is beam. This is middle layer beam. Here, slabs, the Shinkansen or trains will run on this track, okay? This is underground beam. So maybe here is the ground level, okay? This is showing a part of pile, okay, foundation. So Dr. Ishibashi, or in his paper, he or they emphasize that the damages should be concentrated or restricted in columns, okay? If you enhance the flexural strength of columns, okay, the damages will be shifted from columns to beams or foundation, okay? What will happen when the piles, foundations are damaged? You need to excavate and you need to check the condition, okay? Or if the whole structural system are inclined, how can you repair them, okay? It's more difficult, okay? That's why they recommended to consider the structural balance, okay? Considering the easiness of repairing after a mega disaster, okay? So maybe it's a bit easy for you to imagine what will happen when beams are damaged, okay? When beams are severely damaged, the track level, okay, will also be disturbed, okay? So it's quite difficult to repair the damaged upper structures into original condition, okay? Hi. Sorry. That's the basic concept explained in 3.1, okay? But instead of going into very detailed, maybe I should explain some examples about retrofitting methods, okay? That's a very positive content, that's why. Okay. Hi. Starting from here, okay? So, do you remember my picture taken before starting this lecture? Maybe you could see white steel plate, okay? This is steel plate jacketing method, okay? Okay, so in figure 5, steel plate jacketing method is exhibited, okay? So in this case, not white steel plate, colored dark green. So two segments of steel plates are connected here, okay, by welding or a mechanical joint, okay. Sorry, mechanical joint is not explained here, but okay. So which part of the column is retrofitted by steel jacketing? Okay, only from the ground level and till the top of the column below the beam. Okay, so it means that the only shear capacity is increased. Flexural strength is not increased. Do you understand my meaning? If I explain more, if these steel plate are anchored into underground level, underground, the flexural capacity, flexural strength of the column is also increased because this steel plate will act like reinforcement. Do you understand? So if so, the structural balance is lost. The column is strengthened. That's why beams or underground foundation, etc., will be damaged. Okay, that's why only shear strength is improved through this method. It's explained here. Okay, here. This steel plate jacketing method, this method is the most common seismic rehabilitation technique used for railway RC viaduct columns. Okay? Jacketing with steel plate 6 to 14 millimeter thickness enhances the shear strength and ductility capacity. Okay? It will not improve flexural capacity. That's the point. Okay? Hi. But as you can see in this picture, this method needs construction machinery. Okay? Hi. That's why, for example, this one. This is another retrofitting method called rib bar method. Rib bar. It looks like rib bar, like in human body. You also have rib bar, right? Near your stomach. Okay. So this one, rib bar method, doesn't need heavy construction machinery. Okay? Human laborers, human workers can execute this retrofitting in construction site like that. Okay. So what's this? Maybe you can understand in this way. Okay. Shear reinforcing bar, hoop reinforcement. Okay. Startup. Shear reinforcing bar is added outside the column. Well, you can understand in that way. Okay. So by adding additional shear reinforcing bar, the shear strength is increased. By avoiding shear failure, this retrofitted column will show sufficient ductility, deformability. Then it can absorb energy. Okay. Hi. This blue wall is showing this kind of wall in real situation. Okay, so you do not need to destroy all the walls. Okay, just make a small hole to insert the reinforcing bar. So no need to damage the surrounding buildings or structures. That's also one of the merits. Okay. And I will show you another one, interesting one. Then after that, I will stop my explanation. Then I will welcome some questions. Is okay? Right. So this is called a single phase method. Okay. So I guess that the situations in Japan and situations in your country and are different. Okay, but in Japan, especially in city area, the space under the viaduct is used for shops or warehouse, etc. Okay? This is maybe restaurant. Okay, so this is beam, this is column, this is cafe restaurant. Okay, it's showing that it's open. Cafe restaurant Mona Lisa open. Okay, so but these columns should be retrofitted without disturbing the operation of these houses or shops or restaurants. Okay, so how? So only single phase, one phase is open. Okay, that's why this technique, retrofitting technique, was also developed, okay, by a railway company. So a kind of composite retrofitting system. This orange plate is steel plate, okay? And reinforcing, additional reinforcing bars are installed into this perpendicular direction, okay? So, generally speaking, the rigid frame railway viaduct structures will deform in two directions. Okay, so in this direction, this reinforcing bar will act, will show retrofitting performance, and into perpendicular direction, this steel plate will play a role for retrofitting. Okay. So by considering the situations of real structures, they developed very many kinds of techniques, and they adapted appropriate method for each situation. Okay. So up to here, I explained only 3 techniques, but in this paper, several more are included. And of course, besides these techniques explained in this paper, many technology techniques have been developed and applied in practice. Okay. So, here I will stop my explanation first, and if you have any question, I welcome your questions. But I want to emphasize that Japan is located in very difficult geographic situation. Okay, it's natural to experience many earthquakes. Okay, it's a kind of disadvantage. Okay, but we have to live here. Okay, but instead of suffering from earthquakes, we can enjoy, for example, hot springs, etc. Wonderful nature. Okay. So to overcome this difficulty, we try our best and develop new technologies and contribute to sustain a safe society. But we should, I should say, we should enjoy this difficulty, okay, as engineers.
Mr.
So,
Professor,
I can continue,
there are
but
some
maybe
questions.
listening
Maybe
for too long
you
time is also
can.
difficult. That's why, if you have any questions, I will welcome.
Okay.
ちょっと待ってください. Please wait for a while.
Okay. There is some question I want to ask you about
straightforward.
the structure. Okay, okay. You can hear me, okay? Uh, this is from Muhammad. Okay, can we
Be
can see
straightforward.
in
Still,
the okay, okay, thank you. Okay, not
I
still
will
not
change
good
my file.
to hear the, the, the speaker.
Hello? Can you hear me?
Yes, it could be here from me. Uh, okay, you're still change the internet, I think.
Sorry.
Prof. Sudah.
Yes. Can you hear me?
Yes, we can hear you.
Yes,
Yeah.
okay.
I'm sorry.
Okay, you can see can read in the chat room. There are two.
Chat, okay. Many comments.
Okay, I can read the question. I hope
No,
you.
I can read it. I can read it.
This is from Muhammad Febrian Andi from State University of Malang. Uh,
Hello? Hello?
yeah, okay.
Yes,
I
I was.
sorry.
Your voice is clear.
Internet, but
Yeah, hello. Hello.
あの I
And
will
your
explain
voice is
this
clear.
my situation. Okay. Uh,
Okay, okay.
okay. Internet is very terrible. Okay. I don't know why your problem or my problem. I don't know, but I guess that you can hear me clearly. Okay.
There is the question.
But sorry, I cannot hear you well. Your voice is very slow, and
Fabian
Retono's voice is
and
clear to me. But
affiliation.
it's almost impossible to discuss with you, sorry, due to internet problem.
Please help.
Okay, let me
Really?
ask the question for you. Okay, is it okay, Pak
Dr.
Krisna?
Retono's voice is very clear to me.
May I replace your? It's okay. I'm sorry, Pak Krisna.
Oh, yes, yes. I will change.
Actually, okay, I will replace your place, Krishna, maybe for a while until your internet connection is better.
Yes, to please help.
Thank you. Okay. The first question comes from Muhammad Febrian Andi from State University of Malang. Actually, it's different city from this city. So this lecture, there are many students from other cities also, Sensei, and they also give a question here. You can, if you cannot hear my voice, you can just read in the screen his question. The structure ductility index, which applied in RCB in Japan, ductility index is very important to improve additional time of structural failure. According Japan structure standard, how many or how much recommended range or value displacement ductility in RC structure to adequate large deformation cause earthquake? I hope you understand the question.
Yes, yes, yes.
Maybe
Okay.
you
Yes,
give
yes,
the
okay.
okay.
Yes. So
Yeah, please.
I can hear Dr. Retono's voice very clearly. So, but I don't know why, but some voices are almost impossible. Okay. So, okay. So, thank you for your question. Okay. Okay. So I will share one PowerPoint file. Is okay to answer for this question.
Maybe stop share first. Okay.
Now it's share.
Yes.
Yes. Okay.
Yes, okay.
Yes. Yes. Thank you for your important question. Okay. I hope you can see this slide. Required performance for railway. Performance. Okay. I explained in my first session that but railway design code in Japan was revised in 1983. Okay. So before that revision, the ductility was not explicitly considered. Okay. So it might have shown some ductility, but it was not considered in design code. Okay. After the revision of in 1983 in railway design code, it's specified that 4 delta y, okay, 4 times larger than yielding displacement, should be considered. It was specified in that way. Okay, but as you know, the according to the development of earthquake measurement techniques, or according to the increase of measurement devices or sensors, earthquake acceleration, seismic acceleration observed is increased day by day. Okay, that's why now it's specified as 10 delta y. Okay, it might be increased again. Okay, if so, retrofitting should be conducted again and again. Okay, so that's why, as I told you, this special technique, spiral hoop inside reinforcement, longitudinal reinforcement, was developed, and it showed very, very, very ductile behavior. Okay, like 20 delta y etc. Okay, So this performance is much beyond the required ductility in design code. But even when the design code is revised in the future, it can satisfy the requirement. Okay. Hi. Is it okay? Is it sufficient?
Yes.
Retono-san, is it okay?
Yes, yes.
It's a pity that I cannot enjoy a discussion with you due to internet problem. I like discussion and I want to enjoy fruitful discussion.
Okay. I'm sorry.
Right.
Mr.
Go ahead. Or I know that I have received many questions in chat function, so I want to answer to many of you, but
I'm sorry, Mr. Krishna, maybe I can help you. Okay. Should we continue receiving question and answer or?
yeah, maybe I should go ahead. When is the finishing time of my lecture? I heard that 1.5 hours.
Yes, actually, it is.
30 minutes more.
Yeah, still we have many times.
Okay.
So because there are so many
sorry,
questions,
again,
maybe I hope you are your voice. Okay, maybe it is better to share the questions from the screen. So you can just read it. I don't have to read for you. Then after that, you can just answer without hearing my voice or other voices. Is it okay?
Okay.
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 Minta tolong di-share screen. Hope organizer, please share the questions.
Okay. So
Next.
I'll go ahead. So before starting the second session or my last session, let me explain the situation again. Okay. So internet situation is very terrible. So if I listen to the sounds in this lecture room, I can hear my voice again several seconds later. So it's almost impossible to do lecture hearing the sounds. Okay, I should stop hearing, otherwise I cannot continue. And also during discussion, some voices are too slow, and only Dr. Retono's voice is clear. Then again, while I'm answering to the question, I can again hear my voice a few seconds later. Very stupid situation. So, but at least you can hear my explanation clearly, right?
Yes.
If so, it's okay. The minimum level is satisfied. So.
Yes. Okay.
Okay. It's also difficulty, so we should overcome the situation. Okay. Okay. So, okay, I have prepared 2 journal papers. Okay, I will briefly explain the second one. I will spend only 5 minutes. Is okay? はい。ちょっと待ってください。
Okay, please stop share
yes, yes.
the
Please.
committee. Yeah. Prof. Sadek will share the screen.
We are engineers, so we should not complain, okay, for against any situation.
Yes, yes.
Here, can you see this paper? Can you see?
Yes, yes, I can see.
Dr. Retono, can you see?
Yes, yes, I can see.
We can see.
Okay, I see. So this is again this from the same journal, Journal of Advanced Concrete Technology. Okay. The Dr. Arifa Ifat Zerin. Okay, she was a female student from Bangladesh. After getting PhD in Japan, now she is working for Japanese contractors, Sumitomo Mitsui Corporation, the top bridge contractor in Japan. Okay. This is international collaborating research with Professor Hamed Salem from Cairo University, and Professor Amanat was also originally he was the teacher of Dr. Zering in Buet, Bangladesh University of Engineering and Technology. Okay. I will spend only 5 minutes. We investigated seismic performance of RC buildings. Masonry infield RC buildings. So which will be more interesting to you, I think. Okay. I will not go into very detail, but this one, applied element method, numerical simulation method, which is in between FEM and DEM are utilized. Okay. So elements can be separated, okay, by rupturing the springs connecting two elements. Okay. That's why failure process, fracture process, etc. can be well simulated compared to FEM. Okay. So this one, this like frame structures, the masonry infield RC frames. So this wall looks white one, but it's colored. Okay, it's made of bricks. Okay. So after verifying our numerical simulation by experimental results, okay, finally we challenged structural simulation. Okay, like that. Okay. I will tell you only the points. Okay. Hi. We simulated 5 cases. Maybe this is similar to real case, soft story buildings, and RC frames with masonry walls. Okay. But I heard from Bangladesh researchers that in the stage of design, seismic design or design checking, the effect of walls, okay, masonry walls, are not considered. Of course, the weight of walls are considered, but for conservative design, the strength of walls is not considered. Okay, so maybe we should compare the performance between B and C. Okay, so C is the real situation. Okay, B is in design. Okay, so maybe C should show better performance, right? Because effect of walls are included, okay? But the results are opposite. This one, we gave seismic acceleration. I mean, applied scale down Kobe earthquake, so very big earthquake. So 0.3 means the 30% of Kobe earthquake energy, okay, seismic acceleration. So what happened in soft story, okay? Case C, this one. So soft story case, similar to real structures, showed catastrophic collapse only in 0.28 G, okay. Much smaller than case B and in case A. Okay. So I am not continuing this research, but it shows the danger situation of the present design system or design code, which does not consider the real effect of wall. Okay. In this case, I guess that maybe masonry walls showed negative effect of buildings, okay? In the case of soft story building. Okay. 5 minutes have passed, so I will not explain more about this paper, but if you're interested, please refer this paper later. Okay. So I'm not a specialist of building design, but there must be several weak points or to be revised to achieve the real, how do I say, safe performance in real building structures also. I hope it will give some suggestions in your country also. Okay, short topic.
Okay.
Any question?
Thank you. Thank you very much for the interesting. Okay, thank you very much for the interesting research paper. I also read about Miss Arifai Fatzerin in your research gate actually. Maybe we can continue the questions, Sensei. Is it okay?
Or after that, I will give you final session, 15 minutes or 20 minutes.
It's
No, or
it's
I can
good.
welcome some questions.
Okay. You will give a closing session before question and answer? Now or later?
Sorry, pardon?
Do you
Maybe I
want
should
to
continue
give
my lecture.
another 15 minutes? Oh, okay.
Yes. Then finished.
Okay.
Okay?
Yes, please.
Yeah, I'll go back to my lecture. Okay.
Please.
Okay. Can you see this slide?
Yes.
Okay. So in around 15 or 20 minutes, I will give you the final my session, okay, of today's lecture. Again, we have suffered from earthquake disasters many times, and this is a picture after Kanto Great Earthquake. Kanto means the name of region, including Tokyo and Yokohama. So it happened in 1923. Okay. So just like after war, okay, Tokyo City or Yokohama City, all burned. Okay. The 22 years later, so the end of World War II. Okay. So again and again, so we faced very difficult situations, but our past generations or our ancestors overcame those difficulties. Okay, so we should continue our challenge to survive. Okay. Hi. Okay, I'll skip this one. で、in this last topic, my main message is that we engineers made mistake, very serious mistake, okay, in our history. Okay, so we should be humble and we should be based on, we should behave based on scientific fact. Okay, but anyway, we should be humble and we should revise design code. We should improve the social system in sincere attitude. Okay, that's my main message. Okay. Okay. What kind of mistake? Before, allowable stress method was used in design. Okay, it's based on static elastic analysis. Okay, after Kanto earthquake, I explained that it happened in 1923. The next year, seismic force was started to be considered in design code. Okay, so it means that before 1924, no seismic force was considered. Okay, even in Japan. This one, again, shear failure. Okay. Today's important keyword is shear failure, right? We should avoid shear failure. Okay. This is famous shear failure accident in USA. Okay, in 1955. Okay, let's look at the title of this figure too. Okay. But if you're interested in this accident or figures, I can share the paper including these figures. Okay. Let's look at the title figure too. Shear failure of 36 inches deep beams. 36 inches, 900 millimeter, so near 1 meter. Okay. In Air Force warehouse, Shelby, Ohio. Okay. So here, okay, the shear failure happened. This is the picture after shear failure. Okay. So the cause of this shear failure was size effect. Do you know size effect of shear failure? So before clarifying the real cause, I explained that's shear failure, right? So before clarifying the real cause, it was identified that the failure was derived from shrinkage. Tensile mass stress generated by shrinkage, etc. But it was not true. Okay? The real cause was size effect. Okay? So USA identified the existence of shear size effect in 1950. Please remember this year. Okay? So I'm sorry, this figure includes Japanese information, but I added English translation also. So this is the history of allowable shear stress in Japanese design. Okay? Allowable shear stress means the maximum limit of shear stress. Okay? So in design stage, design process, the shear stress should be smaller than this limit, allowable shear stress. Okay. So this is the history. Vertical axis is allowable shear stress. Okay. This is 1930. Okay. So you can find that the allowable shear stress was gradually increased. Okay. So it went to dangerous side. Do you understand? If the allowable shear stress is increased, the real stress generated in the structure is also increased because the limit is increased. Okay. And here, Ohio accident happened already, but still JSC code tried to increase allowable shear stress because by increasing the limit, the design becomes rational, okay, etc. This was a mistake. The many structures were constructed in these eras. 1960s, 1970s is the highly economic growth era in Japan, okay? Can you see this big decrease? Jumping down. So design code was revised into safer side. Okay. So actually this first jumping down was initiated by Professor Ikeda, the Professor Emeritus in my university, Yokohama National University. So I heard from him that all other big professors, except Professor Ikeda, disagreed to this revision. I mean, decreasing shear stress. Okay. So, of course, after this revising, in 1986, second revising, the design was modified into safer side. So after that, of course, the structures design based on revised code became safer, of course. Okay. So this kind of thing can happen in real society or even in academic society also. Okay. Hi. So that's why by modifying the design code, in 1983, startup ratio was 0.2%. The 0.2 is not so large, large reinforcement ratio, but compared to the previous design code, it's much increased, okay, to increase shear capacity. After that, after Kobe earthquake, the startup ratio was increased more, which led to ductile behavior, okay? More ductile behavior. Okay? etc. So now, Japanese seismic design code is being shifted to safer side, better way, better direction. But luckily, we have constructed so large amount of reinforced concrete structures based on bad design code. Okay. Actually, today I explained about seismic problem, but fatigue problem with slab also same. So we made mistake. So very huge amount of reinforced concrete slab were constructed based on bad design code. That's why severe deterioration of slabs are happening. Okay. So now it's also revised. So that's why design code or design philosophy are very important. It will govern the resilience of your society also. So we should feel responsible, okay, for setting design code, and we should be courageous, or we should cooperate together to revise the design code to achieve resilient society. Okay? Without infrastructure, we cannot do anything, right? That's my message. Okay? So maybe I will stop my explanation. I hope you could hear me clearly, but I don't know the situation.
Yes, thank you very much, Professor Akira Hosada, for the very interesting lecture. And actually, as you know, sometimes I also experience your problem. Also, I hear my own voice. But okay, now let's start to the questions from the participants. To the organizer, could you please share the screen? Okay. While waiting. Okay, I will read for you. This is the second question from before this one.
Okay. How do you put the spiral reinforcement inside the column? Okay, it's impossible to use it for retrofitting process for new structures. When you construct new columns, new structures, you can put in a spiral reinforcement. Is it okay?
Okay, yes, thank you very much.
Second, okay.
The second one, regarding the retrofitting method using the reinforcement rebar, do we need to cover entire column height or only the area of plastic hinge?
Okay, a very nice question. Okay. So a very high level question. Thank you. So plastic hinge region, in the case of, can you hear me?
Yes. Please continue.
Okay. So, sorry. In the rigid frames structures, suppose this is a column, the plastic hinge will be generated at both ends, top and bottom part. Okay. The required level for shear strength is different in plastic hinge region and normal region. So we change the denseness amount of reinforcing bars in plastic hinge region and normal region. It depends on the requirement level. For example, the original performance is a bit higher, the less reinforcement is needed, right? So it depends on the original performance. Okay.
Okay, thank you very much.
3.
The third question from the history.
I'm so glad that the audience understand my lecture. So thank you. Number 3. Okay. From the hysteresis curve.
Yes. So it shows that additional spirae may improve the ductility. However, the strength degradation is also severe. How many % is the degradation, and what is your comment about this?
Sorry, I don't understand well the strength degradation.
Maybe Mr. Albert Hansel, you want to ask directly?
Strength. So I don't understand what strength degradation means. Strength degradation.
Mr. Albert Hansel? Maybe not yet. Okay. Okay, it's okay. Maybe later we can discuss it.
Okay.
Oh, he cannot activate the speaker. Okay. Okay. Maybe we can discuss it later. Okay. Maybe now we can go to the next question.
I don't know why, but now internet situation is better, much better.
Better. Oh, okay. Yes. Okay. The next question is Muhtar from University of Muhammadiyah Jember. In Japan, is there a rule for the design of columns with over-reinforced and under-reinforced? Over-reinforced and under-reinforced. Maybe what is the rule if there is that condition? Please.
Okay, so it's a bit difficult question, but now we are checking the performance of each member. Okay, of course, finally we should check the total performance of structure. Okay, so of course over reinforcement should be avoided to achieve appropriate performance, structural performance. Okay, under reinforcement also. So under reinforced also. So if sufficient reinforcing bar, for example, shear reinforcing bar is not provided, it will not show required performance, right? So we are checking the performance directly now. So before, it's a kind of specification. This amount of reinforcing bar should be put, etc. But now we are checking the real performance. Is it okay?
Yes. Thank you very much. Thank you for the answer. Okay, the next question from Ibu Evin Cahya from Universitas Brawijaya. How to ensure the column strength after retrofitting instead of increasing the shear and ductility capability of structure? How we can be sure it will stand on another earthquake, because some damage may occur inside the reinforced concrete column. Please.
Okay. Yes. It's a very nice question. Okay. Honestly, I didn't explain this part in my today's lecture. Actually, in the PowerPoint file, this information was included. Sorry. Okay. If I explain in very easy manner, again, that problem happened. Sorry. So we should increase ductility, right? So if I explain in very easy manner, we conducted many kinds of experiments. For example, changing the reinforcement level, a number of reinforcement, for example, etc. Of course, we need to establish design equation to calculate to check the performance after retrofitting. For example, 4 delta y or 10 delta y, etc. For example, when the requirement is 10 delta y, based on the equation, we will decide the amount of reinforcement, etc. That kind of system is established or provided. To establish those equations, the engineers have to conduct experiment, have to analyze, have to establish a design equation, etc. So today I skip that part. The final information. we can check the performance of retrofitted structures after earthquake, right? So in 2011, 10 years ago, almost all the structures suffered from earthquake, but retrofitted structures survived that earthquake. It's the verification.
Yes, yes.
Okay.
Okay. Yes, thank you very much. Yes, so finally by experiment or by earthquake itself, actually, we can check. The next question is from Mr. Erno Widayanto from Jember University. He asked how we can bridge after installing rebar.
I don't understand.
Okay, me too, actually.
So
Maybe
I should
maybe
answer a second question.
yes, about the installation check plate. Maybe how the
It's also a good
structure
question.
of
Okay. Yes.
yes.
ちょっと待って。I couldn't find the PowerPoint file soon. See this? Yeah.
Yes, yes.
Okay. Maybe his question
Okay.
is how to connect two segments, two steel. Okay. This shape should be connected. Okay.
Understand.
The easiest way is weld by welding. Okay. But
Okay,
welding
thank you very
quality
much
is
for
dependent
the
on the
explanation.
skill of welding workers, right? That's why this
Yes,
is
yes.
another method, mechanical joint. So for each segment, the zigzag shape, a kind of joint is installed. Then by mechanical joint, okay, two segments are tightly connected. So this is also technology development. And it's not dependent on the skill of work. If the welding quality is very poor, the connected steel segment will be separated during earthquake, right? No meaning. Hi.
Yes. Okay, thank you. Thank you very much for the answer. Okay, the next question.
Many questions. Thank you. I feel very happy.
Yeah. Me too. Okay, the question is from Mr. Ahmad Hernadi from Universitas Borneo Tarakan. So it's even another island from not in North Kalimantan. Could you tell Mitigation method could increase cost for repair than unjacket?
You mean
Okay,
the
please.
cost of retrofitting? Sorry, what?
Yes, yes. I think maybe a jacketing method, then of course we have to
Okay, I see.
pay
I
something for
think
that jacketing.
we cannot compare retrofitted one and non-retrofitted one. But if I compare steel jacket method with rib bar method, for example, almost same. But single face method, we need to make a holes, take cores, and we need to insert reinforcing bar. It's much more expensive. So by considering cost and by considering situations of real structure, we should adapt appropriate technique. Of course, it's a total judgment.
Okay. Yes, thank you very much for the answer. Are there still any questions? Okay, from Mbak Ona from Universitas Jember. The structural reinforcement used is to form a spiral. Kind of additional structure when an earthquake occurs and when the train passes at high speed. Because the effect that is obtained is apart from the vibration from the train. There is also seismic, which is not sure where the vibration is.
I don't understand the meaning of question.
I'm sorry. I'm sorry for. We are still learning English, Professor. So
I'm sorry.
for the English. Okay, I will try to. Okay, so actually regarding the spiral reinforcement, yeah, maybe what's the, but I think you already explained it before. Okay, maybe he will learn again from the material.
If I add one explanation,
please.
By installing inside the core concrete inside reinforcing bar is kept healthy. Okay? Core concrete. So core concrete will sustain the weight of upper structures, so it will never collapse. Okay.
Okay.
Without
yes, thank you very much.
If the core concrete is crushed, the column cannot sustain the upper structure anymore. So in a spiral hoop will increase ductility, of course, but it will ensure safety in very extreme situations also.
Yes. So this is the answer for this question, I think. What are the advantages if this place inside the longitudinal? Okay, maybe next question.
Next question.
Oh, are there? Oops. Okay. Okay, the next question, I think I will share my screen. I'm sorry, the slide is actually top. Okay, I will read it. Is it okay? The question is from Alifain Fadila. With the development of regulations regarding earthquakes from year to year, how should we do with existing buildings that were planned in the previous regulations?
Yes. That's also important point, okay? So structures design based on very old design code, we need to retrofit. Otherwise, they will perform well, right? But again, design code is revised, not year by year, but often, right? So that's why inner spiral hoop has advantage. Okay, it's a kind of over specification, but over specification is the best way to achieve good performance. Of course, it's not so easy to get agreement from all players, but that's also one of the problems. Okay? So we engineers should not pursue very economic design, rational design, economic design. It seems nice, but honestly, over spec is the best way.
Yes.
It's not the waste of cost.
Yes, yes.
That's my opinion.
Yes, yes. That's very much important, I think. Thank you very much. The next question is from Mr. Erno. I think he wants to ask directly. Pak Erno. To ask directly to you.
Okay.
Yes, please.
Thank you. Just now, Mr. Sajid explained about the bridge broken. You mean, I mean, the bridge is how can you move it to up to install it when the column of a bridge is broken because the beam go down before disaster. Okay.
I'm sorry.
You know,
I think
what I mean? Only that.
Okay, I'll try to answer. Okay.
I want to know.
Okay, thank you.
So there are many kinds of techniques, methods, of course. Today I just introduced several examples, okay? For example, in our country, carbon fiber sheet, for example, FRP sheet, fiber reinforced plastic, can also be applied. Okay? It's light, much light, not heavy compared to steel plate. So human workers can carry a very light carbon fiber sheet to the site and execute retrofitting, for example. So there are many kinds of techniques. Okay. So carbon fiber sheet is but very expensive. So okay. So depends on situation. But we Japanese people, we Japanese engineers have provided many options, alternatives, so that we can be prepared for any situation. Okay, that's also one of the responsibilities of engineering. It's quite interesting to develop technique in many kinds of limited conditions.
Yes, yes, that's true. Especially the cost budget. Okay. Thank you very much for the answer. I hope Mr. Erno can receive the answer. Okay, let's go to the next question. I think this is the 3 plus. And as a result of the seismic activity on the infrastructure, has happened to the frame viaducts in Hokkaido. Is it possible to repair the damaged building? What the method and what is the advantage and obstacles to repair the building?
Can I share my screen?
Yes.
Okay. It's a good question, and I didn't explain anything about that aspect. We can repair damaged structures, okay? It depends on the extent of damage. This kind of catastrophic failure, okay? We utilize the remained upper structures, okay? In this case, reinforcement cuts and reinforcement of columns is arranged. After that, reinforcement is severely damaged. We will replace. Sorry, we will repair column. After that, if necessary, rebar method, something like that, retrofitting was applied. Okay. So that's totally different, not totally, that's different topic. It will be interesting. Sorry, today I didn't explain a lot.
I understand. Thank you very much for the explanation.
So with high level technology, we can utilize even damaged structures, damaged buildings also. Okay. But if the totally collapse is very difficult. That's why in that sense, we should control the extent of damage.
Okay, thank you very much.
Final question.
Yes, okay, final question.
13.
Yes, in the presentation, it can be seen that the latest development of specification for design is 1986. Any change in specification after that year? What are the main considerations? Maybe about that racing and racing. Please, Sensei.
Okay, thank you. Sorry, it's a bit wrong. 1986 is related to allowable shear stress.
Yes.
So the
Maybe not the same
main
design.
revision in Japan was done after 1995, after Kobe earthquake. Okay. So, sorry, this one, the field of railway engineering in Japan after Kobe earthquake, the required ductility was drastically increased from 4 delta Y to 10 delta Y. This was very big revision. Okay. So of course, even after 1996, some details are improved, but this is the final very big revision.
Okay, I understand. Thank you very much. Okay, I think that is the last question that asked in this lecture. Okay. Now maybe I need to close this session. I would like to thank Professor Akira for inspiring lecture. Very much enthusiastic. So many questions from the participants. I also sincerely grateful for your enlightening presentation. Have shown what's that's important and essential subject, and as take home message, maybe I would like to highlight maybe very small but very much essential point from Professor Akira Hosoda, that generally as civil engineer, as the scientific, as academics, we have to be honest and still stay humble, and we have to act based on the scientific analysis, and also we have to be responsible, for what happened in our academic area. And by this session, I will close today's lecture. Once more time, I would like to say thank you for accepting our invitation to Professor Akira Hosoda, and we also would like to apologize if there are many shortcomings or something that's not very clear, maybe cannot hear or read some questions or hear or something. We apologize, and to attendees, to the participants, please do not forget to fill out the form for certificates, and also I will send the certificate directly to your mail, Professor. Thank you very much. Okay, now it's the time for me to close our lecture today. Thank you for Professor again, and to all the participants for your active participation in this guest lecture. Hope to see you again in the coming lecture from Civil Engineering Department. Thank you. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.
さよなら。
ありがとうございました。
はい、ありがとうございました。It was nice to meet you, Netono-san.
Nice to meet you. Thank you.
See you again.
See you again. Thank
Bye
you.
bye. Thank you.
Lift. Terima kasih Bapak Ibu semuanya atas partisipasinya.
Terima kasih Bu Retno.
Terima kasih Pak
Terima kasih, Bu Retno.
Krisna. Terima kasih. Wah, ini
Maaf
lancar
ya
Pak
tadi.
sekarang Pak. Gak apa-apa Pak, maaf ini.
Ya. Atau internet saya nih.
Ini sudah bagus sekarang Pak.
Ya.